안녕하세요.
안녕하세요. 안녕하세요.
네. 네, 뭐 더 안 오실 것 같은데 시작할게요. All right, let's resume from the last class. So okay, so previously we've talked about how to train logistic regression with maximum likelihood estimate, and I think I've ended the class on a rather uh, a haste note. So before I begin today's lecture, starting from the analyzing the coefficients of logistic regression, does anybody have any question regarding anything from the last material? 혹시 뭐 지난 시간에 한 거 아무거나 뭐 이해 안 되는 거 있으신 분 계신가요? 맥시멈 라이클리후드 에스티메이트를 오늘 이제 그 뉴럴넷 트레이닝 할 때 또 쓸 거기 때문에 이거를 잘 숙지를 하시고 넘어가셔야지 이게 편하거든요. So we're going to talk about using maximum likelihood estimate for training neural networks. So it's it's important that all of you are familiar and comfortable with the maximum likelihood estimate. All right, so since there are no questions, I'll just go ahead. So once you've trained a logistic regression with maximum likelihood estimate and using gradient descent, you can analyze the coefficients or the weights or the parameters, the theta from here, the theta from once you've learned these, you can see which features or which predictor variables are positively correlated to the outcome and negatively correlated to the outcome. So for example, if a certain beta or a certain theta or a certain like ith parameter is positive, larger than 0, then it means that the ith feature is positively correlated to the success, such as usually obesity is positively correlated with heart failure. So obesity, 비만, is positive. Of course, we can all assume that being fat has something to do with getting heart failure, or maybe heart failure has something to do with getting fat. We don't know the direction, but it's certainly those two have like high correlation. And if ith weight or parameter is negative, then that means that the ith feature or predictor variable is negatively correlated to the outcome or to the success. So, for example, we can think of that high income earners are usually not the ones who often get heart failure. So it means that the high income is negatively correlated with heart failure. But so one thing to remember or not confuse coefficients with is that coefficients, so the correlations are not causations. So it doesn't mean that if just because obesity has a positive correlation with heart failure doesn't mean that obesity causes heart failure. There's, as I said, the direction is unidentified. So maybe something else causes a person to be fat and also a person to have heart failure, or maybe getting heart failure, maybe that causes a person to get fat. Like it's not really, we're not 100% sure. So it's just correlation, or some people say it's association, but it's definitely not causation. And this is pretty obvious. Like having a high income doesn't prevent you from having heart failure. It's just that statistically, if you have high income, you're more likely to go to hospital and then get checked up very often, so that you might be able to prevent yourself from getting heart failure. So like, so that's basically what I mean. Like correlation and causation, they're definitely two different things. And like almost all predictive models or even like all deep learning models these days are using correlation. Just everything is association based. Nothing is like virtually nothing is causation based, except for the Bayesian networks. So Bayesian networks are all about causality, but like deep learning models like transformers, BERT, and all that, they have nothing to do with causality. And so yeah, just looking at the betas, looking at the thetas gives you a hint at which features are like positively impacting and negatively impacting, but actually precisely calculating the significance of each feature requires more effort. You need to do like a lot of like t-tests or like some like statistical tests to figure out the actual quantitatively measure the importance of each feature. So that's another story. But so the reason that people say like simple models are more interpretable or explainable is that because you can look at the betas and tell which features are kind of important and kind of not. So and because of this transparency or the simplicity of the model, that is why logistic regression is very, very often used in medical domain. All right, so evaluating the model. So binary prediction requires, I mean, every prediction requires a threshold. So for example, if your logistic regression, if you put a admission record into your model, the trained model, and the model produces some number, for example, 0.3, then we have to decide whether that means a yes or no. I mean, theoretically, our model is supposed to be a probability model. So 0.5 means if the logistic regression model produces 0.5, that means it's a random chance. You have like there's 50-50 chance you end up getting readmitted or not. But in reality, people often like change the value of the threshold to maximize the performance of your model. So like you can set 0.3 as your threshold and say that anything that's above 0.3, any like any samples that that is returned more than higher value than 0.3 by the logistic regression model, then you can say that they are all like yeses, like they're all going to be readmitted. Or you can set that to 0.5, you can set that to 0.7. There's no like strict rule. You usually just set the threshold to the value that you like, because there's a trade-off. Like if you set it to a very low value, then you'll get a lot, you'll be able to retrieve a lot of true cases, but you will also raise a lot of false alarms and vice versa. So people use something called confusion matrix to see the impact of setting your threshold to different values. So this is like a 2x2 matrix or table, and I'm still using the readmission prediction task. So this is the actual ground truth, the actual truth. Like if you have a sample and it's either readmitted or not readmitted, so that's the actual class, and your model will make a prediction whether the sample will be readmitted or not. And depending on like which spot you land on, it's either true positive, false negative, or true negative. So if your model predicts readmitted and it was actually, and the sample or the patient was really actually readmitted, then you've hit the true positive corner. And if you say that the sample will be readmitted, but it was actually not, then that's a false alarm. So it's called false positive. And if you say the sample will not be readmitted, but it was actually indeed readmitted, then it's a false negative. So it's also bad. And if your model predicts the sample will not be readmitted and it was actually not readmitted, then it's true negative. So depending on the task, I mean, there's always a trade-off. You either increase this or increase this, and there's a whole other theory, like which is type 1 error and which is type 2 error, and in order to decrease like which type of error you need to increase the sample size and all that, like that's all like statistical theory. But basically, I mean, intuitively, if we're thinking about cancer prediction, for example, so if you're given a patient record and you want to predict whether the patient will have cancer or not, which is like a fatal disease, then you want to minimize the false negative. You don't want to miss the cancer patient, the patients who actually end up having cancer. You don't want to miss them, because anything that you miss will most likely lead to like death, mortality. But false alarm, false positive, if you raise a lot of false alarms, then you're virtually not, you're not killing anybody. Like, you're not making a prediction that leads to a death of a patient. So, but it does incur a lot of effort. Like, you're wasting resources on, like, if you have a lot of false positive, that means like you make 100 predictions that, like, you see 100 samples and you like say that all of them will have cancer patient, and when in reality only like few of them will actually end up having cancer. So you're like raising a lot of false alarms, and that leads to like unnecessary tests and unnecessary time consumption. You're consuming a lot of time resources, human resources, if you raise a lot of false alarms. But it doesn't. But that is how you prevent people from dying, actually. So there's a trade-off, and it's a hard problem, basically. And in order to minimize both errors, the only sure positive way to minimize both errors is just increasing your sample size, like basically using big data. All right. Okay, so based on these TP, FP, FN, and TN, there are different types of measures or different types of metrics that you how you evaluate your predictive model. And of course, the most famous is accuracy. So accuracy is basically the denominator is all cases, and the numerator is the ones that you actually got right. So true positive and true negative. So it's among like of all the samples, how many times did you make the right prediction? And this is, and people use this for like multi-class classification very often, like ImageNet. Like, you have a picture and you want to classify what type of animal you see in the picture. That's like a good way to use accuracy. If the classes are balanced, like if you have like 10% dog, 10% cat, 10% elephant, 10% giraffe, like if the classes are balanced, then accuracy is surely a nice way to go. And in our case, if we're using a data set where 50% of the patients or admission records are they end up in readmission, and 50% are not readmitted, then it's a balanced data. And in that case, it's okay to use accuracy. But if you're using an imbalanced data set, for example, only like 10% of your 10% of your samples are truly readmitted, and 90% are not readmitted, and if you use accuracy, then it's not a really good measure, because if you always say no, like if you always say like not readmitted, not readmitted, not readmitted, then you're gonna miss those 10 cases. I mean 10% cases, but you're still gonna achieve 90% accuracy because you've got the 90% right. So that you don't want to use accuracy when your classes are imbalanced or your data set is imbalanced. So in order to avoid that kind of issue, there are some alternative measures such as precision, sensitivity, and specificity. So precision is that out of all the samples that you said are positive, like the ones that you predicted that will be readmitted, you want to count the numbers that you actually got right, the true positive. So that's the quality of your prediction, basically. And sensitivity is among all the actual positive cases, among the actual readmitted cases, how many did you actually retrieve? So sensitivity is sometimes called recall in information retrieval sense. So like how many, like if you have like, if you're given 100 cases, 100 samples, and 10 of them are readmitted, then if you predicted like 9 of them to be true, and if you missed 1, then your sensitivity is basically 90%. And specificity is what's called a true negative rate. So it's kind of the opposite of sensitivity. So So the denominator is now all the like negative cases, all the negative cases, and among those negative cases, how many did you actually get right? So that's specificity. And I mean, you can assume that you can easily infer that there will be other types of like measures. Like if you say, if you can have like TP plus FP as a denominator, then FP or FN or whatever. So you can basically you can combine all of these to make up all different kinds of measures. But basically these are like the very famous ones, and you can mix them up to actually get a more comprehensive evaluation metric, which is called AUROC. So thing to note is that in order to calculate precision or accuracy or sensitivity, all of these, or basically in order to calculate any of these, you still need to have a set threshold, a fixed threshold, because in order to say something is positive and something is negative, you need to make a prediction, and making prediction means like you set some number like 0.3 or 0.5 or 0.7 as a threshold. So in order to do all of these, you need to have a threshold, and you can easily expect that the precisions or sensitivity and any of these will change as you change the threshold, because these are all like the functions of your threshold value. So in order to avoid that issue, you can actually continuously change your threshold from like 0.1, 0.0, 0.1, 0.2, all the way to 0.9, 0.95, 0.99. Like you can like integrate out your threshold, integrate these functions with respect to the threshold. So that's what's happening here. So this is called area under the receiver operating characteristic curve, or area under the ROC curve, or AUROC. So people use AUROC a lot. I'm pretty sure a lot of you are already familiar with this. So it's basically a plot between a TPR, which is true positive rate. So true positive rate was sensitivity. So how many, like among the true cases, how many did you actually predict right? And or basically how many did you successfully retrieve? And the x-axis is false positive rate. So false positive rate is actually 1 minus specificity. So 1 minus that means like Tn plus Fp. So yeah, so the numerator will be Fp instead of Tn, which is 1 minus this. So how many, like how like many times do you raise a false alarm? That will be the x-axis, and then you sweep across a whole different thresholds like 0.1, 0.2, 0.3, and this is how you basically plot the AUROC. So if you have if you set a certain threshold, then you can get a certain like false positive rate, and at that specific false positive rate, you can have a specific true positive rate, and that's how you basically plot this curve. And this is called AUROC, which means area under the curve. So area under meaning that like this so let me see. Yeah, basically like all areas under here, that's your AUROC. So the larger the AUROC, that means the higher, the better your model is performing. And if you have 0.5 as your AUROC, which means that like this is 0.5, right? So this means that your prediction, your model is doing just basic random guesses. So it's just as good as random guess. So you want to be better than AURC. You want to be like at least 0.7 or 8 to say that your model is doing something meaningful. And interestingly, if your model performance is below 0.5, like 0.3 or 0.2, 0.1, that also means it knows something. It has picked up the pattern. It's just that it's predicting in the wrong direction. You can see what I'm talking about. 0.5 is the random guess. So anything above or below means that the model has picked up a pattern or a signal. It's just that if it's above 0.5, it means it's making correct predictions very often. And if it's below 0.5, it's just making wrong predictions very often. So all you need to do is just invert the label or the outcome to make it positive. All right, moving on. So the problem with there's another problem with the AURC, which I will get to in a minute. But before that, I'll just let me introduce another measure, which is called AUPRC. So it's area under the precision recall curve. So before, this was a plot between true positive rate and false positive rate. This is a plot between precision and recall. So recall is still a true positive rate. So I'm just using the same y-axis here. That's now an x-axis here. And precision is what I showed you guys here. So it's a precision and recall curve. And of course, again, you set your prediction model, you set your threshold to into a various values, 0.1, 0.2, 0.3, all the way. And then you plot this, and then you can, again, calculate the area under this curve. You can just integrate them out, or you can just do like numerical approximation. So thing to note is that AUPRC value of 0.5 is much better than random guessing. It's actually very hard to achieve 0.5 AUPRC. You can see that it's because the precision is what makes it really difficult. Like here, true positive rate and false positive rate were using different denominators. So they were totally separated out. So because the sensitivity or recall is using TP plus Fn as the denominator, and false positive rate, which is 1 minus specificity, is using Tn plus Fp. So there is no overlap in the denominator between sensitivity and 1 minus specificity. But in here, you're using precision and recall, and they do have a slight overlap in the denominator because precision is using TP, recall is using TP. So it's really hard to like achieve a high AUPRC. Yeah. All right. Yeah. So you can see that this line here is that line is what tells you that is as good as a random guess. Before it was a diagonal line, but now it's like fixed. It's attached to the bottom. So anything above 0 is actually just doing it's doing something. Anything above 0.1, like even 0.1, I mean, anything above 0 means that your model is picking up a signal. So 0.1 is still picking up a signal. All right. So AURC, what's the difference between AURC and AUPRC? So AURC is less sensitive of class imbalance. Means that so there's a pretty famous paper by Saito and Ramsmeyer in 2015. It's the paper that shows that as you change your ratio of true positive samples and negative samples, as I said, like readmission 10%, not readmission 90%, you can change the ratio to like 20/80 or 30/70, 40/60, and you can show that the AUROC doesn't really change as you change the ratio. So it's less sensitive. It's less aware of the class imbalance compared to AUPRC. AUPRC will change like crazy as you change, if you like meddle with the ratio of true the positive cases and negative cases. So people started to use both measures, AURC and AUPRC, when they're doing binary prediction in like machine learning research papers. Some people often use both metrics. And yeah, and it's really hard to get a better AUPRC under imbalanced classes. Like if we're talking about the very rare cases, like out of like millions of samples, only like 10 or 20 or maybe like few of them are positive cases, then it's really easy to achieve a good like low false positive. I mean, so false positive is 1 minus specificity. So if you minimize, I mean, if you maximize specificity, I mean, maximize the true negative rate, that means you're going to get good AURC. And it's easy to get true negative rate when there's like when we're talking about very rare cases, because you just need to virtually say no most of the time, like no readmission, like 99% of the time. If that's actually the case in the true data, then you're gonna get a very high true negative rate, meaning very low false positive rate, and that's gonna help your AURC. So yeah, when your data is severely class imbalanced, you might think about using AUPRC instead of AURC. So, and F1 score is another thing that uses precision and recall, and it's a harmonic mean of precision and recall. Like there's like harmonic mean, like 조화 평균. So, and it's still, and because it's not a sweep over different thresholds, it's still you still need to have a threshold. But people in the information retrieval domain very often use F1 score, and information retrieval meaning like among millions of documents, you want to retrieve only a very few documents that are relevant to your search query. So F1 score can be used in that sense. All right, so that completes our supposedly what I wanted to cover in the last class. And before we jump into the deep learning material today, is there any questions so far? So what we've covered until now, all right. There's a message in the chat. So how can we finally decide threshold? As far as I understand, AURC is a function of threshold and giving us how much our model is trained well, yes, but does not give us which one is the most. Exactly, so that's a very good point. AURC doesn't tell you which threshold is the best threshold. That's totally up to you. So you can see, like as you increase your threshold, you'll start to, so when your threshold value is very low, you'll start something like something around here, like here, and then as you increase your threshold, you'll go like somewhere over here, and it's up to you whether you want to put more weight on minimizing the false alarms, or whether you want to put more weight on getting the true positive rate, which is maximizing the recall. So it totally depends on the application or the problem that you're solving. Some people use the threshold value that maximizes your F1 score. So because, as I said, F1 score is a function of the threshold. So again, your F1 score will change as you change your threshold, and at some point, there will be like a diminishing return. So as you start increasing it, like 0.1 threshold will not probably get you the maximum F1 score, but again, 0.9 threshold will also not get you a maximum F1 score. Some value in between 0.0 and 0.9 obviously will give you the maximum F1 score. So you might want to use the threshold value that actually gives you the best F1 score. That's what you can do. All right, did that answer your question? I hope it did. Okay. All right, so what I've gone through with this whole like 0. So in this lecture, 04 prediction part 2 is the basics of logistic regression and how you can train them and how you can evaluate them, the model. And it is very important that you are familiar with all these, because all the following material, like the deep learning neural networks, will be building upon this. And the actual assignments where you need to train your model, you need to evaluate your trained model using either AURC or AUPRC. Of course, you don't have to integrate all of them, but at least you need to know that they are the proper like evaluation metrics. Okay, so moving on to today's material. All right, so today's topic will still be modeling, but okay. So before we jump into the deep learning approach, I should actually touch upon how to actually implement logistic regression, and which is just to use the one that already exists. All right, so what Sci-kit learn is what you should all be very, very comfortable with if you want to do anything remotely related to machine learning. So, by the way, Okay, so maybe I should have taken a poll, but oh, maybe I can take a poll. I think all right. Polling. Add a question. Okay, this is not very convenient. So let's just forget about it. I thought I was going to be able to do like a quick poll, but I guess it takes more effort than I expected. So, so who here who has never heard of scikit-learn or never used scikit-learn before? Like, is there anybody here who has never used scikit-learn, not even once? Okay, so I guess everybody. No. All right, so maybe a couple people. Okay, so I guess it's a good idea to then just briefly go through what they are. So scikit-learn is let's see. Basically, you can do all kinds of machine learning. You can use all kinds of machine learning technique except for deep learning. So this is what you should be using all the time when you're not doing deep learning. Now, and also when you're using Python. So this is a Python library that will enable you to use any type of machine learning model or statistical model except for deep learning. So because deep learning is a whole different issue. So for example, if you're interested in doing decision tree, it will have decision tree. See here, like sklearn tree, decision tree classifier. No, there is also decision tree regressor. So yeah, so and it always have this. They always, like all the different models, machine learning models in scikit-learn, they always have the same method, same class member functions. So you always call them, and then you use something. Where's the Okay, that's not very good because this is not a very good example, right? Anyway, so let me just, so what scikit, you can just install scikit-learn using Linux and Linux pipe, or if anybody already has installed Conda in their system, in their machine, then they probably already have scikit-learn. Wait, so I forgot to, is there anybody who doesn't know what NumPy is? Maybe I should have asked that question first. Like, who don't understand anything about NumPy, and any like just, or who's not really comfortable with NumPy, the concept of NumPy, or has anybody who's never heard of NumPy? Anybody? Okay, so everybody is at least familiar with NumPy then. All right. So to me, NumPy is exactly the same thing as MATLAB. So if anybody has used MATLAB, then the NumPy is the same thing. It's just how you manipulate vectors and matrices and like multidimensional matrices in Python, and it has almost the same operation, like functions or as MATLAB. And so scikit-learn runs on top of NumPy. So you have you have like training variables, like training data represented as NumPy matrices, and you can use scikit-learn to train your model on top of your vectorized NumPy training data. So you install them, and then basically once you've installed them, you just need to, for example, if you want to do logistic regression. So there's linear model logistic regression. You click this and then see how you can use this. There's all kinds of like different parameters, but you can get to that later. So very simple example right here. So you have, so for this is where you okay, so you obviously you need to import the model first. So you import the model logistic regression, and this is for importing your training data. But in our case, we're going to build our training data by pre-processing the Mimic3 data set. So you'll come up with your own X and Y, basically. This function loads, I mean, in this example, they load iris data set, which is like a flower data set. And instead of doing this, we're going to do readmission prediction. So we're going to have our own X and Y, X being the matrices where each row is a single admission and the columns represent different features like ethnicity, gender, not age, gender, or diagnosis list or medications list. So that will be our X, and our Y would be a vector of readmission labels, like whether each sample was readmitted or not. So you'll have your own X and Y, and then you just call logistic regression with default values. You can have like all kinds of different ways to initialize logistic regression, which kind of like regularization you're going to use, whether you want to use like dual form, whether you want to like change whatever. You don't need to do any of these. Like logistic regression will just work out fine with even if you don't tune these parameters. You just call them like this. You just call it and train them. So fit means estimating the parameters. So you have X and Y, so you can train your model. So fitting is training. And then given a new test data, you can make a prediction. So this is how you predict. So in this case, what this guy does is just taking the first two examples from X and feeding them into your trained model, the CLF classifier, and making it predict. And basically it says the output is 0 and 0. Or yeah. So yeah, predict is using a threshold, but you want to output an actual value like 0.2, 0.3, or some continuous value. So doing that will be predict probability. So yeah. And then you can calculate the score, how good of a fit your model made, given a training data, given like a input and input and the label. So this says that it has a score of 0.97. I think the score here means just accuracy. So you want to do something. You want to use AURC or AUPRC instead of simply doing this. So very simple. You just call it, train it, and make it predict. And then when you make it predict, it'll give you a bunch of like y hats, the predicted y's. And once you have the true y and the predicted y's, then you can calculate AURC. So here, AURC. Maybe AURC is not the right area under the receiver. All right, receive operator. Okay, so here it is. All right, here. So there's a function. Of course, obviously there's a function that calculates the AURC score for you. So you don't need to calculate them yourself. And all you need to do is just provide a true y, so the actual labels, and the predicted y, the 0.2, 0.3, whatever, some continuous value that comes out of your logistic regression. So it's a vector and vector, and you can just forget about all of these, because we're going to do a simple binary classification. So all you need to provide to this function is just these two, and then it'll return to you a number that is the AURC score, the actual area under the curve. So yeah, so for example, the true variable, the true value, I think in this case they're using 4 samples. So true labels of the 4 samples is 0, 0, 1, 1, or not readmitted, not readmitted, readmitted, readmitted. And let's say your logistic regression model outputted 0.1, 0.4, 0.35, 0.8, and then you can plug these numbers into simply this function, and it'll return 0.75 as the AURC score. It's very simple, right? So very, very simple. Just you set up you pre-process Mimic3 to get the X and Y, and then you call the logistic regression function, train it, and then make it predict, and then plug the predicted value into this function, and you'll get an AURC score. Like the whole thing will take less than like 20 lines or 30 lines. All right. So basically, this is how I recommend that you do your assignments, which will go out probably maybe early next week. It'll be a very simple pre-processing and fitting your logistic regression function on top of your pre-processed data. Any questions so far regarding Sci-kit Learn? No. Yeah, I recommend, like, I assume that all the attendees of this class is at least interested in machine learning or like doing data analysis. So I strongly recommend that everybody get really familiar with scikit-learn. All right, so that was scikit-learn. So we'll jump into deep learning approach then. So, okay, so there's a message. Oh, okay, I see. Okay, I'll try to do that. Maybe I can do it now. What? Say this. All right. Maybe I need to. All right, give me just a second. I can try to upload it right now. Yeah, I usually make the slides the day before the actual class because I don't have any material. There's no material called Machine Learning for Health online. There's no textbook, so I'm just making this as I go. So I usually make it the day before the lecture. So that's why I haven't uploaded it beforehand. Okay, let me just upload it real quick and then I'll return to you. All right, I just uploaded the slides for today on Classroom. So anybody who wants to have their own copy for taking notes on top of the slides, then you're welcome. I mean, yeah, please go ahead and download them. All right, I'll just return to the material in a minute. All right, should we get started then? Everybody got their copies? I hope so. So Okay, so we've just covered scikit-learn, and then we'll jump into today. I initially thought we might be able to cover recurrent neural networks, which will be the first model to use in in the future, but I thought it might be better to cover the very basics of neural networks, how to train them using backpropagation, in case there are people who who have never heard of backpropagation, maybe, or people who know it, but people who know it on the surface level and just don't understand how it's actually done in practice. All right, so let's jump into the material. So neural networks consist of something called neuron, when the neuron is basically what looks like this. It's a nerve cell in our body, and just like neuron, where neuron gathers electric signal from these like branches, and then if that electric signal is higher than some threshold, internal threshold, it'll fire up another signal, and then it'll that signal will be passed through this axon, and then will get propagated to other nerve cells through this synaptic terminal. So it's gathering is done here, and then the firing and goes here, and just like this. So it's a binary action. It's either fired up or not. There's no continuous value in neuron. Neuron is either fired or not, it's activated or not. So it's just like that. There's artificial neuron, which is also, it kind of resembles the structure or the mechanism of actual neuron. So that's why it's called artificial neuron. And just like the previous neuron, where it gathers the electric signal from the branches, there are branches here that gathers signals, and the signals are summed up internally, and then it goes through some activation function to decide whether it's fired up or not. So typically this activation function used to be a binary variable, because as I said, neuron is either fired up or not. So we want to resemble that. So we wanted to make the neurons, the artificial neurons, also binary, whether it's fired up or not. So that's why people used sigmoid function as an activation function to make it binary. But these days they use ReLUs or PrelUs or LUs or all kinds of different kinds of stuff. Anyway, so the electric signals, instead of actual electric signals, it's just that the input, there are inputs, multi-dimensional, multivariate input, and each input will be multiplied to the weights or the parameters or the thetas, and that's how and then you sum them up. That's how you get the signals summed up here. And there's usually a bias. So these are all actual variables, but you also want to cancel some bias off by having a certain fixed value that's always added to the neuron. So that's where the bias comes in. And in our case, we can think of x's as the admission representation vector. So it's just a vector that I borrow from the previous line. So if you guys remember, it was like a 40-something dimensional vector where the first three represented what? Admission type, like emergency or elective or other. And the next five was marital status, like divorced, single, married, whatever. And the next four was ethnicity, and so on and so forth. So you can assume that I'm plugging this vector as an x, and then it'll be multiplied by all different kinds of weights, and then you can sum them up here, and then it'll get fired up. And if you use a sigmoid function here, so because as I said, it's either fired up or not, so sigmoid function, which looks like this basically. So it's either if your summed up value reaches certain threshold, then it'll be very close to 1 here. And if it's below some value, like if you go there, it'll be very close to 0. So that's how you make your neuron binary. So if you gather a bunch of signals from your input data, x's, and then you sum them up, and then it's like above certain number, like 0.5. I think this was like 0.5 or something. it'll be very, very close to 1, meaning that your neuron is fired up. And if you think about it, if you think about replacing the x's with your input representation vector and replacing the activation function with sigmoid function, then what that is exactly a logistic regression. So that's why I told you guys it's important to understand the previous material. What a single neuron with activation function, with sigmoid function used as an activation function, that is exactly logistic regression. And I hope this is pretty evident to everybody. Basically, you're replacing this x with a vector x inner product with the vector of parameters, the theta, and I'm just skipping the bias part, but bias is always there. So yeah. Okay, so I hope this is pretty clear. And so a single neuron is a logistic regression, and if you start adding more layers like this here, or adding more neurons, that becomes more complicated than logistic regression. So before, what I did was without the hidden layer, without this, you just plug these in these input directly to the output with sigmoid function as the activation function. That was logistic regression. And now I've added a hidden layer. So the hidden layer is what makes neural networks more complex or more expressive. So so now there's the input layer, which is this input layer, and there's hidden layer between the input layer and the final output layer, which is the output being the binary value. So you can intuitively see that this will make your model more complex than logistic regression, and more complex means it can approximate more complex function, basically. So it has more capacity to learn complex patterns from your input data. Before, what logistic regression could do is, it was given your data, it was able to linearly approximate or linearly model your training data. But now this is a non-linear model because you've added a hidden layer there, and you have like different like activation functions. So in this case, now it can model your data non-linearly. So yeah, so it's more, it is more expressive, basically. And of course you can add more hidden layers. I'm using just one hidden layer here. This as an example, this is just one hidden layer, but there can be 2, 3, 4, maybe 10, maybe 100. These days people use like 50 or 100 in ResNets. All right. Okay, so in order to mathematically formulate your neural networks to show how you can, like, represent neural networks as a mathematical form, and then like learn the parameters by doing maximum likelihood estimation through backpropagation. So I'm going to use this example from onwards. So the input will always be this, the admission representation vector with 40,000-ish dimension. And the hidden layer, I'm just going to use four neurons. As a hidden layer, it's just a hidden layer of 4 neurons here. And the output will be, of course, binary. It'll be a Y. All right. So you can assume that there are weights tied from one input to 4 hidden neurons. And each neuron will have its own weight connecting to the output variable. So in this layer, between the hidden layer and the output layer, there's 4 weights or 4 parameters. And in this case, there's 4 here, 4 weights attached to the first variable or the first dimension of the input variable. And of course, another 4, and there'll be a lot of 4, like these like sets of 4, until you reach to the very, very end, which is the 40,000-ish index. So you can assume that between the input layer and the hidden layer, there will be 4 times the size of the input dimension, which is 40,027. 3 plus 5 plus 4 plus 1 plus 14 plus, that's 27, and then there's 10K, 20K, 10K. So that's 40,000. So it's 4 times 40,000, 27 parameters between input and input layer. So that's a lot of parameters that you need to learn. And there's only 4 here, but there's like a lot here. And you can represent the weights as a matrix actually, because it is kind of structured. Each variable, or I mean each dimension, has 4 weight connected to the hidden layer. So you can visualize this as a 4 by 40,027 weight matrix. So it's a very like narrow but long, like tall matrix. And how you can visualize this actually being processed in your computer mathematically is that it's just an inner product. So your input variable, or your admission representation vector with 40,000-ish dimension, will be a vector, and then it's basically a vector times matrix multiplication. So if you have this, and then you can multiply this with this, and this with the second column. Again, the input variable with the third column, input variable with the fourth column, and then you'll end up with like a 4-dimensional vector. And when you think about this, when you actually think about this weight matrix, each weight matrix has a corresponding like a subset. For example, these are all 0. Like most of them will be 0. This will be a very, very sparse vector, because you won't like these first few are categorical variables. Categorical variables, as I told you, is they can only take one value at a time. Like you can't be both white and black according to this categorical variable. And also there were some multi-label variables such as diagnosis lists and medication list, procedure list, but you're not going to get like 10,000 different diagnoses in a single admission. So it'll be a very like most of the like 99%. 99% of this vector will be 0, and only few of them will have 1. Like only very few indices will have 1, and there will be like corresponding column, or actually this will be a row. So corresponding row in this weight matrix that corresponds to the actual the values that have 1, the indices that have 1. So in this case, this 1 will correspond to this, and this 1 will correspond to this, and then there will be some row corresponding to this one, and some corresponding row that corresponds to some diagnosis codes, some medication codes, some procedure codes. And so this will be a representation, like this 4-dimensional vector will be responsible to represent this value, which was emergency, I think. So I think the first was elective, second one was emergency, third one was other. And in this case, the marital status, I think the first one was single, married, widowed, divorced, and other, I think. So in this case, this red row will be the one that represents, so this is 4, so divorced basically. So this semantically means divorced. So like you can see what I'm getting at here. So like there's like an embedding or corresponding row for each feature, and a lot these will not really matter in our case, because like this has 0. The first index is 0, so this will all be zeroed out. The third is also 0, so this will also be zeroed out. So you only need to retain the ones that actually have the ones here. So yeah, it looks like this basically. So only a very few of them, few rows in your weight matrix will be activated, or will take part into calculating the final output. So and as I said, so here, once you do like inner product between your input and the weight matrix, you'll get a 4-dimensional vector. What that actually is that the same operation can be done by summing up the red, the active rows. You can see that it's the same thing. Like if whether you do an inner product between the vector and the weight matrix, or whether you take the ones that have the actual, take the rows that correspond to the indices that have 1 as a value, and you sum them all up, it's the same thing. So you sum them all up, and then you'll of course be left with the 4-dimensional vector, because you're summing up like this and some other one, some other row, some other row, and some other rows, like very few number of rows among all like 40,000 rows. You're summing them out, and then you get this, like the summed row. And you can think of like it's basically this, so that row, that summed row, corresponds to this hidden neuron 1, 2, 3, 4. And then of course this is not the end, because as I said, there's got to be an activation function. Like all neurons have an activation function. So in our case, I showed you guys before that we are going to use sigmoid functions. So this could be a sigmoid function here. So just summing them up, summing your weight matrix was not enough. You need to push them through the activation function for each neuron. So it's a coordinate wise or dimension wise operation. So once you do that, then you actually, now you are left with a hidden representation. You've done the inner product between the weight matrix and the input, and then you've put them through an activation function, and now you have the output of the hidden layer. So that's your hidden, you call them hidden representation. And then you put it through. So this Y is not just a single, you need to obtain this Y. So having this 4-dimensional vector, you want to convert them to a final like 0 or 1 binary variable. So in order to do that, you need to again multiply each neuron value, each like yellow value, by the weight, and sum them up, and then put them through a sigmoid function, and then get a final 0 or 1, or not 0 or 1. It'll be like some value between 0 or 1, like 0.1, 0.2, 0.8 or something. So at least this part is very familiar, very similar to logistic regression. It's just that instead of you put this into a single neuron or a single node, you put a hidden representation, the 4-dimensional vector, into the single node, and then put it through a sigmoid function. So there's difference between this and the logistic regression. All right, so yeah, okay, so this is what we call a hidden representation. And in our case, we were using, as an input, we were using admission representation vector. And we put it through a hidden layer and put it through an activation function. So now this is what we call a hidden admission representation, or latent admission representation, because this is kind of like hidden to us. I mean, it's not really hidden, but we don't know what it really means. It'll be some number, like it'll be like 0.2, like minus negative 0.5, negative 1.7, and positive 2 point something. It's really hard to understand what it means. Like this is easy to understand. You can see like because there's 1 in the second dimension, this means it's emergency. And then because there's 1 here, it means that this guy is divorced. And because this guy is white. You can literally interpret this representation. But here, this 4-dimensional vector, it's hard to interpret what this really means. So that is why it's called latent or hidden admission representation. All right. Okay, so yeah, this is just a comparison between logistic regression and neural network with a single hidden layer. So before, it looked like this. So you have the input vector, 40,000 dimensional admission representation, and you put it, you multiply a weight like different thetas or different betas, according to our previous example, like beta 1, beta 2, beta 3, beta 4, all the way to beta 40 something thousand, and then you sum them up and then you put it through a sigmoid function. That's what logistic regression is. But here we're converting this input vector to a hidden representation vector, and then putting that through the sigmoid function. So now you can see why it is still a admission representation. It's now, instead of explicit representation, this is hidden or latent representation. So yeah, you can still do like clustering and stuff. I mean, if you're familiar with clustering, you can do clustering with this actual like raw value, but you can also do clustering with this, because this is still a admission representation. It's just it's a 4-dimensional vector instead of 40,000 dimensional vector. But you can still do like clustering, or you can do visualization on them. You can do various kinds of things with them. All right, so okay, so far this was the forward propagation, like how when you have a input data, you can like put it through a hidden layer, and then put that hidden layer through a final layer, the output layer, and then get the final output. And in order to get a meaningful number out of this, you need to have the proper set of parameters, like the 4 parameters here and 4 by 40,000 weight matrices here. You need to, they need to have like a correct value in order to make a correct prediction. So training is what will let us do that. So before we get into training, is there any question? Anything you want me to repeat in Korean? Anything need for clarification? All right, let me get some water. All right, so training. As I said, we need to estimate the values of all parameters, which is 40,027 plus 4 parameters. Yeah, like here and here. And for the sake of mathematical derivation, we're gonna use sigmoid function as the activation function for the hidden neurons. So like these 4 these 4 H1, H2, H3, H4. These hidden neurons will be using sigmoid function as the activation function. And of course, because we want the binary outcome, this will again be an activation function, like sigmoid activation function. Okay. All right, so like repeatedly, I'm saying this is a binary classification problem. And because of that, we're gonna reuse all the like likelihood functions, log likelihood functions, and all that we covered from the last lecture. So just like a quick refresher. So the likelihood function for a binary classification problem will look like this. So this is, as I said, this is a Bernoulli distribution. So if there are like n number of samples, and each sample will have index I, then you can multiply all of them, multiply the likelihood, or the Bernoulli distribution, like the likelihood of all the samples independently, because they are independent samples, and you put a log in front of them. So you put log in front of this, and then you get a summation of the likelihood. So it's a log likelihood function with averaging out by dividing the whole thing with the large n. The large n being the total number of samples that you have. And yeah, so this is the log likelihood function. And as I said before, we need to minimize negative log likelihood function, NLL, with gradient descent. I mean, that's what we did with logistic regression. And it's the same principle in here as well, in the backpropagation. So the negative log likelihood function will look like this. So yeah, so what happened here is that you put log in front of the PR, which is this. And if you put log in front of it, let me annotate. All right, if you put log in front of here, then this will become a summation, basically. So it'll be like sum of log of, so this h theta xi was the logistic regression function before, but now this will be just, let's just say this is the prediction itself. The prediction being like the y hat. So it'll be y hat I with the actual y. Before yi was a true label, and this was the predicted label. So this, I'm just replacing h theta xi to a y hat. So this is y hat time raised to the power of yi, and then it'll be 1 minus y hat again, I raised to the power of 1 minus the true label y. Yeah, like this. Yeah, this sigma looks a little weird. Okay, like basically like this, and then there will be like averaging out term here. And because there's log here, you can put like you can separate this part with this part, and then you can put the exponent in front of the base. So that's what's happening here. Basically, you do that, and then you'll get this right here. So if anybody's familiar with cross entropy function, this is cross entropy function. So yeah, we've derived cross entropy function starting from the Bernoulli distribution. So all right. So what it means is basically you want for the samples that are labeled 1, this will survive. For the samples that are labeled 0, the negative cases, this will survive. And according to which which sample, negative or positive sample you're dealing with, you want to either minimize this or this. Okay. All right, moving on. So this is so we'll start from, this will be our objective function. We want to minimize all the parameters with respect, I mean, we want to minimize this with respect to all the parameters. So this will be our objective function, or sometimes it's called cost function. All right. Okay. So for example, if we want to update, so each variable, each parameter will be updated independently. I mean, one at a time using the gradient descent update rule. So yeah, actually this should be a negative probably because we're doing gradient descent. But anyway, so when we're updating W1, it'll we'll be doing it according to this rule. So the next iteration of W1, or the new value of W1, will be the old value of W1 plus the step size or the learning rate times the gradient value. So gradient value being, it's a partial derivative derivative of the objective function, the NLL here. So yeah, this is the NLL here, and with partial derivative of the NLL with respect to W1, the one that we want to update. So basically you need to calculate this. A little more complicated is updating this one. So I've just used the notation W's for all the parameters here and V's for all the parameters here. And as I said, the V parameters will be a 4 by 40,000 matrix. So I'm just using like 1, 1, 1, 2, 1, 3. So all the parameters that is attached to the first dimension will be like V1, 1, 1, 1, 2, 1, 3, 1, 4. And all the parameters attached to the second dimension will be like 2, 1, 2, 2, 2, 4, 2, 3, 2, 4. Basically, it's just like a matrix indices. All right, and in order to update this, it's the same rule. You have you have the old value, and you add to the old value a step size times the partial derivative of the NLL, the cross entropy term, with respect to the parameter that we want to update. And you can assume that intuitively, this will be easier than this, because this one is attached right directly to the outcome. Like y hat is just a logistic. You can think of y hat as a logistic regression output with respect to the input of W, like input from here, like the hidden representation are weight summed with the weights W1, W2, W3, W4, and pushed to the and put through the sigmoid function. So that is like the logistic regression of the hidden representation, basically using hidden representation as the input value. So you can assume that it'll be rather easier compared to actually updating the ones that are like in the down below. So right. We got only 10 minutes. Let me see. We wanna, in order to cover this, we should probably just derive a simple like backprop rule. Maybe show you guys a simple chain rule. Maybe I can just derive this very quickly. This term, yeah, this term here. Yeah, I'll just call this as a loss function between like, y hat, because this is a function between the predicted value y hat and the actual value y. So I'm just going to call this the loss function, like L of y, y comma y hat, and this will virtually become like a partial derivative of loss function with respect to W1. I'm just going to use W instead of W1. All right. And you can break it down. I mean, just like in the logistic regression, we can break it. Oh, I guess I didn't show you guys how to derive the derive the gradients from the logistic regression function. So I'm just going to use Z. So y hat is our output, but before y hat, there's something. I'm going to use Z as the value that is summed up here, and y hat now will be, so some notations, y hat is a sigmoid function of the Z, and the Z will be W1 times H1, H1 plus W, whoops, W2, H2, and et cetera, et cetera. So it's like et cetera, et cetera, et cetera. So you can break down it, you can break this derivation into a, just to make it easy, the loss function with y hat, and then y hat with respect to Z, and then Z with respect to the actual, I should use W, actual, the actual weight that we want to do, we want to derive, do the derivative with respect to. So you can break it down like this. The reason we do this is because this just makes it easier. So this part here is just the cross. You can simply do, you can forget about all these. Let's just take one sample at a time, and then you can do derivation. You can do a derivative of this function with respect to y hat here, which will look like, so this will look like y hat negative y over y hat 1 minus y hat. It's very simple. You like y, you do derivative with respect to y hat, then there will be like y in front of y over y hat 1 minus y over 1 minus y hat, and you get the negative out, and then you do like algebra, and you'll get this basically, and this will now become, it's a sigma. You're doing what you're doing. So what's happening here is basically like what's happening is this. So you're just doing derivative of the sigmoid function with respect to its input, which is y hat 1 minus y hat. So this follows from the fact that derivative of a sigmoid function of x with respect to the x is sigmoid x and 1 minus sigmoid x. This is just the nature of sigmoid function. So if you do derivative of a sigmoid function with respect to its input, it'll be a sigmoid times 1 minus sigmoid. So that's what's happening here. And then this is very simple. Because z was just a like a weighted sum of the hidden output h1s and the weights. So and all the others will be irrelevant because you're doing partial derivative with respect to w1. So only h1 will survive. So it'll be h1 here. So this is our value for this basically. So it's very simple, like because y hat will be some value, it will be 0.1 or 0.3 or whatever, and y will be either 0 or 1. So you can calculate that. And then again, y hat will be 0 point something, y hat 0 point something. H1 will be the previous will be the output of the hidden neuron, the first hidden neuron. And you know this value because you've like you can calculate this by doing like some by doing the weight sum of the input and the v variable, the v parameters. So you do that, and then that will be your gradient, and then you can plug that into here, the sum value, and then you multiply it by step size, and you can do that. So, all right. So moving on to the next one. So wait. Oh, that's weird. Okay, so all the things that I drew on the slides will persist. Okay. Maybe I can just erase all of this then. Okay. Okay, just one more quick derivation. So now we're going to try to derive this. So before, okay, it's very inconvenient. Okay, so before we broke this down into 3 parts, so we also need to break this down into a few parts in order to actually see how we can derive this, and that would be V11 VL would be, the first few parts are very similar because we are starting from top to the bottom. So we again want to do like a y hat here and the y hat here with respect to the z. The z was what was accumulated here, the weighted sum, and sigmoid z with respect to h1 and h1 with respect to, so h1 is the output value, the actual weight, the activated value of this neuron, but there's also the summed up value of this neuron before the activation. So I'm going to call that G1. And then there's, so G1 will be the weighted sum of like weighted sum of all the variables with the like V11, V21, V31, V41, V4. Like it'll be a weighted sum between the input and the output, input variable and the hidden neuron, and the weight matrix is here. So it'll be G with respect to V1, comma 1. Right. So the first second two parts are similar. Like this and this is reused here, and all you need to do is just calculate this and this and this. So to rewrite this, I'm running out of space. Y one minus y hat. Again, y hat 1 minus y hat And now we don't need to do this because we're not updating W1, so we're actually doing this instead. So Z was the output, and H1 was the one that actually consists that consists of the Z, because Z was W1 H1 plus W2 H2. So if you do derivative of Z, partial derivative of Z with respect to H1, then what you're left with is obviously W1. So you put W1 here, and then H1 is a sigmoid of G1, because G1 is the pre-activation value of this function, of this neuron. So you can think of H1, you can obviously see, just like in this part, it'll be a H1 times 1 minus H1. As I said, this comes from the nature of sigmoid function. So we've covered this part, and then now this part, G1 is G1 here is the x1 times v1 comma 1 plus x2 times v2 comma 1, and so on and so forth, all the way to x 40,000 something. And because this is partial derivative, you don't need to care about all these. You only need to care about this. So this will become x1. So yeah, so this is how you derive this. Yeah, so again, you can calculate all these, like the y hat value, you know the y true y value, you know the W1 before updating W1. So the old W1 value, you know that value. H1, you know it. So you can calculate this, and then x1 you already know it. X1, well, in here x1 is 0, so it doesn't matter. But in some cases, if x1 was 1, then this whole value will take meaning, and then you can update your v11 according to this value. And you can see there's some parts are recycled, like this part here. This part here is recycled, and because of there are certain parts that you can recycle when you oh, it's already 33. So okay, I'll just wrap it up here. We can pick up the other parts from the next class. So if you start increasing more layers, this was just one single hidden layer, but if you start increasing hidden layers, then there are certain parts that you can recycle, as I've shown you just before. And that's how you can like start from the top and go back to the bottom and do back propagation, because you're using some values that you calculated at the top layer, and then you're reusing it down below and down below and down below and down. So the whole thing could be recursively defined, and that's how you do back propagation. All right. Okay, so all right, thank you for listening. And is there any quick question regarding the whole derivation that I did so far? It's pretty like a straightforward math, but I hope that was not too bad. If not, I'll see you guys next Tuesday, and I'll try to release this assignments. Yeah, we'll announce the assignments next Tuesday. All right. Thanks very much. Bye-bye. Bye-bye, guys. Have a good weekend.